So it's a pleasure for me to introduce to you the next speaker, who is Chris Rackauckas from MIT. I'm pretty sure that everybody who is working with Julia knows him for his outstanding work. For those of you who might not have heard of him, I would like to use Harald Binder's three parts, methods, education, and application of data science in order to introduce him. So first of all, education. So who is Chris Rackauckas education-wise? Well, he is applied math instructor at MIT. He's doing a great job there. If you want to, you can go to YouTube and watch some of his courses there. In terms of methods, he's pretty well known for combining differential equations and neural networks in all kinds of ways. And I am pretty sure that he will show us some of his applications. So with this, yeah, looking forward to your talk, Chris, and hand over to you.
Okay. Yeah, thank you very much. So yeah, what I want to talk about today is exactly that, the use and practice of scientific machine learning, because, I see that this is an AI group and, a lot of people have seen, these standard AI techniques, but there's really a change going on in the way that AI is being used within scientific contexts. And that change is really by incorporating scientific knowledge into the process. And so I want to kind of go through, how is this being used? Why is it being used? Like, why would you not use just a standard neural network instead of these other types of techniques, and then also go into some of the practice of it. So what's going on behind the scenes in terms of the package development, the methods research, just I can give a whole overview of what's moving in this field. So the key behind scientific machine learning, right? Like if there's one high level idea that you pull away from this, the real idea is that what you have as information is not necessarily always captured in data, right? So think about Einstein's gravitational laws, right? I mean, what's the data set? What's the 3 million or the 3 billion row data set that you can use to give a neural network information about Einstein's laws, right? Like, that's a weird question. There is no data set for that, right? Instead, there's 30 different scientific experiments, or at least at this point, probably hundreds of them, that kind of show that general relativity should be true. And that's captured in an equation, or it's captured in these mathematical models. It's captured in these differential equations. And that is information, right? It's information that's not necessarily data. And so what we want to do then is say, well, there's a certain amount of information that we need to get to in order to have a good prediction. And with scientific machine learning, we want to come up with ways so that way we can supplement the information of data with the information of models. So why not just use a pure model? Well, if you've done a lot of physics, then you know that you always have to make approximations, right? You always make the approximation that the pendulum angles are not going to be too high. You make approximation that your friction terms are going to be linear, right? There's always these approximations made. And if you allow yourself to mix with machine learning, then you can kind of get these nonlinearity aspects as well, right? And so if by using the two together, the idea behind scientific machine learning is that you can compensate for both of their weaknesses and build something that is stronger than either on its own. Now, how do you actually get there in practice? So I want to talk about the two aspects of that, right? So first of all, the application. So what are some ways that scientific machine learning has been used? What are some problems that it's solved so far? But then I want to go into the software aspects and kind of discuss what is it behind the mathematical methods that needed to be, what is the impetus that makes it so that way 2021 is the year to do scientific machine learning? What has changed? What's needed to do this? But what's also the things that we need to be able to do it better in the near future? So first of all, what are some methods of scientific machine learning and the applications? So here's one that we've been making use of a lot of in many different contexts. This is the universal differential equation, where you can embed neural networks into some partially known model, right? So if you made the entire thing defined by a neural network, that'd be a neural ODE. But the key here is that it's not like you don't know anything about your system, right? You know a lot about your system. You can model the helicopter with just its first order terms and know a lot about the first order terms and just say, well, there's some nonlinearity that we don't know about, right? There's some extra thing that is missing from our model that is required to be able to capture the full behavior. And so what this is allowing you to do then is to say, let me specify as much of the mathematical model that I know, as much of the physics, as much of the biology that I know, but let me learn about what I possibly don't know. And in fact, when you mix this, you can then mix this with symbolic regression, right? So then you could say, once I've learned this neural network, right? Once I've learned the missing functions of my model, what I can do is I can do a symbolic regression and be able to say, well, what did the neural network actually learn, right? If I was to have wanted to write down that model in the first place, what would I have had to write such that I get the same prediction as the neural network based one? And so then this can give you what mechanistic terms you are missing to then be able to predict what possible mechanisms, right? So, if you interpret this back as in a mechanistic model, a term X times Y means that there's an interaction that, and the interaction between rabbits and wolves causes more wolves. It's like, well, that makes sense because of the feeding. So yeah, I mean, so what you then get from all this is you get a way to be able to impose all the knowledge that you have, to be able to hopefully make the machine learning process more data efficient, easier to fit, et cetera, and then be able to use that to get back to a mechanistic model because you never strayed too far away from a real interpretable model, right? That's the idea. Does it actually work in practice? Right. I guess one extra aspect is that before we go into some of the practice is, you can even extend this to the probabilistic domain. So that way you can say, let's fit neural networks inside of as missing terms inside of differential equations. And we can do this with the Bayesian types of methods. So that way we can get a posterior over neural network weights. But every single time we sample that posterior, that gives us a possible extension to the model that we should have been doing. And then you can even do symbolic regression, right? So this can give you, say, a probability distribution over terms you should have been adding to the model in order to correct for absences in the data that cannot just be found with different parameters and such like that, right? So that's the real key. It's finding something structural that should be different about your model, and it's imposing this prior information. And you could do it, in a deterministic way or in a probabilistic way. And there's all these different ways that it's being developed around that. But I guess the big key is, the idea makes sense, the intuition makes sense, but does it actually work in practice like that? So I think that the practice of scientific machine learning has a very nice story through what we have seen a lot with COVID-19. And so I want to kind of showcase a lot of the results from that lens. So, everyone knows SIR models. If you didn't know SIR models before, now since 2020, you do. But one of the things about these SIR models, right? Susceptible goes to infected, goes to recovered. It's missing a lot of details about extra things like, well, quarantine, right? Like, someone is quarantined, then they're not necessarily someone in the population that can be infecting other susceptible individuals, right? So one of the things that I had this student that actually taught a lot of these SciML tools to. The pandemic hit, and he was suddenly just like, well, if we just do an extension to the SIR model where we learn, where we allow ourselves to have a quarantine, but this quarantine is a neural network which is based off of the SIR, right? So it's basically like, people read the statistics of what's going on in the country, and as the infection rates go up, they will change their quarantine behaviors such that there's more quarantine imposed, right? If that's the simple assumption that we have, how predictive of a model can we actually get from this? And so that was what was put together, right? This is what we call the QSIR. It's this neural network embedded extension to the SIR model. And the interesting thing that we show in this paper is that it's close enough to a mechanistic model that if you actually look at what happens with the Q term, the quarantine that we learn in this semi-mechanistic way, the quarantine actually has its inflection points around a day or so away from when the actual quarantine was imposed in the countries that we're modeling, right? So we trained this country by country by country by country. I think it looked at around 100 different countries. And there's just this pattern that the quarantine that is being learned here in this semi-mechanistic model matches the true quarantine behaviors if you go look at the news reports of what's going on, right? And so this is telling us then that it's learning something that is truly realistic, learning something that is interpretable and mechanistic. But then the next thing we need to do to validate this is really find out, is it also predictive? And so what we then did was we went to some synthetic data. So we said, okay, let's go to models that are not SIR, and how predictive is a extended, SciML extended SIR model. How predictive of that is to other models of quarantine-induced epidemics, right? So you can go to these 9-compartment models, which are like 11 ODE models, and you could go to this SIR-HD model, which is this model that was captured being actually used for a lot of these predictions within Sandia National Labs for United States, right? And if you go to these more realistic models that people were developing for predicting COVID, right, and we just said, well, what if we didn't spend any time modeling, right? What if we just had this QSIR model? We just did SIR plus Q thing, and neural network goes in there. To be able to learn how to extend the SIR on its own, how close can we get to the more predictive models, right? And here in the red, we show what happens. This is the training part, and the prediction is fairly close. And now the real key, though, is is the mechanism helping at all, right? Is the mechanistic assumptions of scientific machine learning, does that actually do anything? And if you look at what happens with just a real, just a pure machine learning method like the neural ODE, you see that it does not have the same behavior, right? In fact, there's a lot of other things that are going to be false about the neural ODE, which need to be true about the pandemic. So here you can see that the forecast goes to, this is a normalized population amount. So it's the percentage of the population that is infected, right? And the percentage of the population that is infected goes above 100% for the pure neural ODE form. Well, it's because a neural ODE just says that this is an ordinary differential equation. The QSIR model says S goes to I, goes to R, goes to T. They should always add up to 1. Right? So these things that should be true about the model are all imposed, and so it seems like in some sense that we have it mathematically captured, but in a lot of numerical exercises have really captured in practice. It seems that mechanistic those mechanistic properties and enforcing enforcing things that to be true about the model, like conservation of people, conservation of energy, all these things, by imposing that within the learning process, you can learn from the same amount of data, you can get much better predictions. And so we're able to show, on many different extensions to this model, on many different versions of epidemic models, we can show them that a very simple epidemic model with non-mechanistic extensions, learned through this, neural networks embedded, we can get some very good predictions, even though pure machine learning methods cannot extrapolate that well. And we can show that it's very robust, even having small amounts of data, because of a lot of these facts that we know need to be true, like conservation of people, they're all imposed by the model form. And so then we were able to take this and say, well, if we can actually learn how, if we learn something that's interpretable, if we learn how quarantine has changed, right? What happened at this time as we were publishing these papers was that there's a bunch of Trump rallies that happened in the southern United States, and a lot of states suddenly basically turned off their quarantine protocols. A lot of these governors said, well, quarantine is ramping up, and so now we cut off quarantine, we're going, no more masks required, et cetera. So, a big thing happened in the United States. And when we train the QSIR state by state in the United States, we see exactly that change, right? We see that quarantine goes up. And on the day that the stay-at-home order expires, the quarantine drops dramatically, right? And so this then, since we now have a semi-mechanistic model with interpretable pieces, we can then ask the question of, well, what would a counterfactual have been? What would have happened if the stay-at-home order did not expire? What if we had changed the policy? What would have happened differently in the United States? And so you can justify this then, because all of the pieces are pointing to that this has learned some form of a mechanistic model, and it's able to make some accurate predictions. So now, if we were to take this and say, let's keep the relative Q the same instead of dropping it at the day that it all expired, then we can actually go back through and make that be true about our network, and make that be true about our model, and actually get predictions for what the case range would be. And then so we actually published this then in a health data science journal that was just a whole bunch of predictions about what would have happened differently according to the policy. And I think that this is really the key, that wraps up this epidemiology story, because the first pieces were about can we have a method that is working well and everything, but then this is really the last step that was like, is this useful? And, so we took it to the epidemiologist and showed all the evidence that we had behind it to say, this is what we believe the mean case reduction would be, given this kind of scientific machine learning approach, because of this associated mechanism, because of what we can do with this kind of model and its predictability. And in the end, this was accepted as a way to be able to, capture this quantity that would tell you about the real world effects of a policy. And you can get to this real world effects of policy. There probably will be studies that will get there in like a year or two or so, right? But a lot of other approaches would require like a very strong modeling effort with people really sitting down to build a predictive model by hand and then perform this counterfactual on that model, right? But what we're able to show is that we can get there now fairly quickly by using semi-machine learning with semi-mechanistic model approaches all combined together. And so that's why I feel like this really wraps like a nice bow around that story. Now, to go back to some of the pieces around here, though, that we started looking into next, right? Can you actually start to recover the full sets of differential equations in ways that's imposing all the laws that you would expect to be true? So here, for example, this is a nice small case to write down. So here is a SARD model of an epidemic, right? Susceptible goes to either infected or, but infected can either die or recover, right? So this is one of the standard models. Now, instead of remember that one of these issues with the neural ODE is that it allows the number of people to go to infinity, right? So there's no restrictions on that model. But can we build if we don't have too much idea of mechanism, but if we have some idea of just the interaction graphs between our different states, can we impose that and use that to be able to help our learning process? It turns out that you can, right? Because if we have smaller neural networks, we can say, well, there's some interaction term within this causal model, which makes S turns into I can turn into R or D, and so this makes it so that way the graphical connections are correct. An ODE that is defined by this thing will have conservation of its values by definition, right? As long as things stay positive, et cetera, et cetera. But this makes it so that way, even if we did not have much form of mechanism, we can still impose a lot of things that we know about the process. And what we show then is that if we train the neural networks in this form and do the symbolic regression that I mentioned before, turning neural networks into symbolic terms, we can actually directly recover each of the bits of the model in a way that is fairly data efficient. We can use like 15 or 20 data points to be able to do this full recovery process. And so we're going to be putting out a preprint fairly soon that is showing the data efficiency of these methods and how the data efficiency changes as you include more or less mechanistic information. But the key really is that the more mechanistic information you have, the more predictability you can get from less data. Now, in some of these cases, you can come up with some other ways to try to predict the quantities in here. I want to talk about something that we just got an award for this week at the American Congress of Pharmacology. That's about the use of these scientific machine learning cases for accelerating clinical trials. And so, what the key behind the clinical trials is that you want to get patient-specific predictions of some dynamical system. So what does that actually look like? So when someone walks in the clinic, they have this set of covariates like weight and sex. Those go into a structural model, which tells you how to get the dynamical parameters of some dynamical system, where the dynamical system in the end tells you exactly how the drug concentrations will change for each individual in the body, right? So this is what's known as the nonlinear mixed effects model, and this is the standard. This is the gold standard that is used behind pretty much every single FDA drug release that goes on. Now the key here is that in the structural model, there are two pieces. There's eta, which are the random effects, which are patient specific, which means you need to understand the patient to know how they will differ, and then there are the theta, which are what's known as the fixed effects, which are the same across the population. And the more you can capture in the fixed effects, the more you can capture in the theta, the more the more that you'll be able to predict how individuals will react differently to the drug based off of just simple information like weight and sex, right? They can walk into the clinic, or they can look at the label on the drug, right? So if you know about the drug labels actually are discovered through this nonlinear mixed effects process. And how that all comes forward is, you find these fixed effects that try to capture as much information as possible. So what that means mathematically is it's this maximum likelihood problem where you want to find the theta, the population parameters and the per patient parameters, such that on average the per patient parameters are not doing anything, which is basically like saying that you're capturing as much as possible in the population estimates, right? So this is how everything is done today with these clinical trial simulations. And my work in Puma says, we're working with all these different groups like Pfizer and Moderna and such. This is the process that we've seen everyone been using. Though the interesting thing that's been happening is that these models are something that is very much unknown. Now, why is something like weight and sex? And there's actually 5 covariates that are generally used throughout different drugs: weight, height, sex, ethnicity, and fast metabolism for a given metabolite. The same 5 things are always used because it's very difficult to ever get a structural model of what's going on within the body, right? So, technically people today, you can always get everyone's genome, but no one would know how to use your genome to be able to predict how you'll act differently to a given drug, it's specific at the specific level of the drug dynamics. And so generally all of those extra factors that we could be using for patient predictive medicine, they're all left out. And so, and not only that, but also the dynamical model itself, like, the actual physiology of how the drug is interacting with the body and then the patient's response to the drug, that also is a model that takes a long time to find. And so one of the things that really holds back clinical trials these days and really makes the process slower is the fact that these models are hard to get, and you can only understand these models for a small number of potential covariates. Now, the idea, though, is that, well, I mean, we can, the scientific machine learning method, as long as you can train neural networks in any scientific model, which is a big asterisk that we'll get to at the end of the talk here. But if you can train neural networks within any given scientific process, then why don't we make the neural networks be a stand-in for the missing functions that we don't know here, and use them to be able to do discovery of the best structural model with respect to this really weird maximum likelihood constraint, right? So what we can do then is we can replace this structural model with a neural network where the weights of the neural network are the fixed effects of the model, right? So basically saying, like, can the train this so that way the neural network is capturing as much as possible of the prediction of how the dynamical system will change with respect to different change in the covariates, right? And because this is now astructural, you can make your covariate list be, it can be an entire genome data set, it can be entire RNA-seqs, it could be images of an eye during macular degeneration. All these different pieces can then be used as the full predictive nature of how someone will react differently to the drug. And then you also can include the neural networks within the dynamical systems to be able to learn about the physiology that you could have been missing. And so this is actually something where we are, not all of the information is released yet because this is being shown on a clinical trial for macular degeneration. But it's what we can find from this is that this can actually recover and get one of the most predictive models fairly quickly through this process, right? And so we're actually putting this into practice then within this Pumas AI software. So I also have an industry position working with pharmacology. And so one of the things I did was I built Pumas AI and this Puma software. But we now have it such that you can put astructural neural network models within the pharmacometrics pipeline, right? And use this to be able to train these missing models, and then be able to do this recovery. And at the end of the day, it actually spits out in LaTeX inside of the official reports the symbolic version of the model that it has discovered. It says, this is the model that we discovered. This is the mechanism that this would be associated with. And then this is how this is giving you different patient predictions. So this really, so this is something that's still somewhat a bit in progress, though. If you see something a few years down the line where your label on your drug says you have to get an image at this imaging center and then have it sent through a convolutional neural network to be able to tell you what your dosage should be, this is the formal process by which that is going through. And so so these scientific machine learning things, right? Both the predictive power is useful here, but also the interpretability is very major here, because you need to be able to say why someone should be drugged differently or dosed differently, and that interpretability step in the semi mechanism allows you to get there. So now let me go into a different aspect of scientific machine learning. Here, we're using it within climate modeling. And the key is that, you want to model the entire ocean with a climate model, but you can't really represent the ocean as a whole bunch of three-dimensional partial differential equation solves, right? So because three-dimensional partial differential equation solves are hard, so you can't do 10,000 of them all simultaneously. So how do you define a simplification of this model that gets the correct thing that you can run a whole lot of them in parallel? That's the key behind building this climate model. So, the one I'm specifically talking about is the CLIMA project, which is the MIT plus Caltech new climate model that's being built in Pure Julia. So, there's different ways to be doing this, but one of the standard ways is to create what's called a parameterization of the ocean model. So you take large eddy simulations and you want to find an approximation to the Boston-Ness approximated Navier-Stokes equations such that you can learn a one-dimensional partial differential equation that describes how the heat is flowing vertically through this model, right? So you want to average over a box and you say, I don't care about the X and Y here. I just want to know how everything works just in the Z axis. And let me then just put a bunch of these little boxes of just Z axis heat flows. And now, that would replace three-dimensional partial differential equations with one-dimensional ones. And everything in your life should be good after that, right? Well, how do you actually do that process? So if you were to take this model and you take the Boston-Ness approximated Navier-Stokes equations, you do an integral along the XY plane to be able to take the average with respect to X and Y, you would get this equation without this neural network in here. And so this is called the convective adjustment for ocean parameterization. And so this is one of the standard ocean parameterizations that were being used in a lot of these climate models. And so because we're working on the scientific machine learning stuff in the same lab and everything at the same time, we looked at this and said, well, the issue with this convective adjustment is that it's an approximation to the vertical heat flux, right? So this W prime T prime bar is really just, this is the average heat flux in the Z direction. And the reason why you do this approximation is because this equation doesn't define W prime T prime bar. So you'd have to, what it actually comes up with is it gives you another partial differential equation that defines that. But that partial differential equation is missing a term, which, so you actually have an infinite cascade of partial differential equations. And so this is, if you know this, this is called a closure relationship where you say, well, we can't solve infinitely many one-dimensional partial differential equations. So we approximate this by a term, which comes from some, there's some theoretical arguments as to why this is a good version of the approximation here. So what we thought was, well, we can take the best approximation that people know about using and currently use in climate models. We can say, but it's not capturing everything. So let's capture the residual, the extra bits with the neural network. And so this actually starts to get us towards like the software and the training methodologies, because what we can say is, well, how do you actually train a neural network within a climate simulator, right? Well, what you can do is you can say, if I take data from this three-dimensional simulations, I can get what the vertical heat flux is. I can then subtract out these other terms by looking, I could take the data, I could take the differences in the data, subtract out this little bit, especially since you already know this parameter. And whatever is left over is this residual that I should capture with the neural network, right? So you can take your data, you can then munge your data to be able to be the data for this missing term of the neural network, and directly train the neural network on that data. And then once you've trained the neural network, you stick it back in your model and you say, how well did this actually learn? And that's what I'm showing over here. And it works a bit. It works kind of, right? So the blue is what the three-dimensional partial differential equation is. If you just look at the vertical axis as temperature over time, and then this is the orange is that just this one-dimensional PDE trying to capture that one piece, which is the simpler model. And it seems like it almost works, but you have a drift over time in the errors. The errors seem to always be growing. And why would that be the case, right? And this really gets to the heart of the difficulty in scientific machine learning, because the reason why is because we took this neural network and we trained it against the data outside of the model, and then we stuck it into the model. And the problem with that is that we have essentially controlled with a neural network how the derivative should look. And then we saw that there was a drift over time in the solution. And if you've ever done control theory before, you should have a light bulb light up right there that you're like, oh, we've only controlled the derivative and we saw drift. Well, what do we need to be doing? We need to be controlling the integral. So how could you control the integral instead? Well, if you were to have the solution of this partial differential equation be the thing that you're putting inside of your loss function instead of the flux term, then what we find is that the model that we're able to learn from this is actually the most accurate parameterization we're able to come up with, right? This is a very accurate parameterization, and this is actually the one that we're then proposing to put into this new climate model. So that difference then is really that the loss function is on the solution of the partial differential equation instead of on being a part that is trained separately. And that then gives you a methodological issue, right? Because this means that the standard training flows of, I take a neural network against data and I train it. You cannot necessarily do that because the climate simulation itself has to be a part of the loss function, and then it has to be part of what you're back propagating through. So you need to make sure that everything that you have, your entire scientific model, is always differentiable with respect to the weights of the neural network. And this is true about all of the examples that I gave before. Now, you might think that, yeah, that's not hard, right? There are ways to be able to differentiate an ODE, right? So, for example, let's take the neural ODE paper, right? That neural ODE paper shows how you can, one way that you can differentiate an ODE. Let me double check how much time I have left here. All right, yeah, going to the 30. Okay, yeah. So this that neural ODE paper shows how much time, how you can differentiate an ODE, and the process is essentially like this. You can solve this ODE forwards, and there's a little trick that if you solve this ODE from Tn to T0, that will actually solve backwards. I'll get into numerical things in a bit, right? In mathematical theory, if you solve this ODE forwards, then you solve this ODE backwards, you get back to the same spot. And so you can use that to always know at any time what your real process was going forwards and going backwards. And turns out if you solve a separate ODE defined in a very specific way, what comes out at the very end is the derivative of the ODE solution with respect to parameters. So if you have a black box ODE solver and you need to differentiate through an ODE solve, you can solve an ODE forwards, you solve an ODE backwards, and a bit of the thing that comes out in the end when you go backwards is that derivative that you would have wanted, is that same derivative that you can count as the back propagation of the ODE solver. Great, so that solves our problem, right? Because how do you do gradient descent on this loss function? Well, the derivative with respect to the neural network embedded climate model, you just use this adjoint technique, and this gives you the derivative there, and now you gradient descent, right? Turns out that there's a lot more involved in that, and so what are some problems that show up? Well, one problem is if you actually just take a linear ODE, right? So you solve it forwards with lambda, and then you solve it in reverse with minus lambda. If you do this on, say, Euler's method or something, what happens to the error here? You see that as lambda decreases, as lambda gets more and more negative, you actually have exponential growth in your error. And if you want to see the derivation of that, that's a very simple derivation you can find in the stiff neural ordinary differential equations paper that is already released now. So this process that I said is mathematically correct, right? If you solve forwards, then you solve backwards. It is mathematically correct, but it is numerically unstable to the point where you get exponential growth in your error, and 10 to the 30th error in your gradient is probably not a good idea, right? So that's one issue. The other issue is that approach, it's solving some extended ODE. That ODE has size states, whatever the forward solve is, it's number of states, number of ODE weights, right? So it is 2 times states times the number of parameters, where parameters is the number of neural network weights, right? If you're doing this on a stiff ODE, like something that comes from a Navier-Stokes equation, using that kind of technique requires doing linear solves within the solving process, which then gives you about a cubic scaling with respect to a few things. And so now you have, so this way of calculating your derivative gives you a derivative calculation which requires the amount of time that is cubic in the number of neural network weights you have. That means that a first order optimization method has the cost of doing something equivalent to doing like Newton's method for training neural networks, right? And people always use first order methods in machine learning for a good reason, because cubic scaling of really large numbers is not very good, right? So this shows us that, you know, if we really want to be able to make scientific machine learning a reality, you can't just use a very naive adjoint approach. You really need to care a lot about how this derivative is calculated, because a lot of things can go wrong. In fact, if you go back to that climate example, I can actually show you that the reason why we stumbled onto this is because we found that adjoint method, that way of calculating the derivative, is unconditionally unstable on the climate model, on that climate example. For any delta t, it will actually give you exponential growth in your errors. How can something mess up so bad like that? Well, let's just take a look at it, right? So the simplification of the problem that we're looking at is to just look at an advection equation, right? And in your PDE course, you'll teach to your students that when you discretize a advection equation with finite differences, right? There's two directions that you can do this first order term to, right? You either take the upwind direction or the downwind direction. And you need to choose a direction because, well, if this wave is moving to the right, you better be using the information from the left. Otherwise, you won't have the information behind you to be able to carry it forward numerically, right? And so if you do the von Neumann analysis of the stability, the forward solve of this advection equation is only stable if you choose the correct upwinding direction of the discretization, right? And that should give you immediate pause, because if you're going to solve this ODE forwards, right, you solve it with upwinding. If you solve it in reverse, then the wave is moving the other direction. And so the only version of that which is stable is to have used the other discretization. And so what that essentially means is that if you just try to use that adjoint technique of solve forward, solve backwards on a discretization of the advection equation, what you'll find is either you have unconditional instability and exponential error growth in the forwards direction, or you have unconditional instability, exponential error growth in the reverse direction for your gradient calculation. And so this shows you a very simple example to say that, you know, you can do a lot of things that are mathematically correct in terms of backpropagation, which are not numerically correct. And so there needs to be something that really handles all these numerical issues. So that way you can, you know, the ways that you do machine learning today, where you write down a neural network and you say PyTorch gradient, right? You know, there needs to be something very sophisticated done, so that way you can do that in the context of scientific machine learning, and that is the core mathematical problem behind it. Right. So, I mean, if you do, you know, if you're someone who does engineering, right, you've probably learned stiff ODE solvers, and so, you know, but you learn in class implicit Euler, but then you learn implicit Euler sucks and you never want to do it. You know, implicit Euler and Crank-Nicholson are never actually used in practice because they're really bad. You call ODE 15S, you call CVODES, and these things are magical and they'll solve all the real hard issue for you, right? So in the world of ODE solving, stiff ODE solvers took a very complex problem and they made it tractable to a very large audience by giving a software that was able to handle it well. And what we really identified from these scientific machine learning problems was that something similar needed to happen for scientific machine learning, right? So when you have stiffness or when you have chaos and all these different properties, there needs to be something so that way you can just call a software, ask it for a gradient, and expect that with the right choice of method, you'll get a gradient that is fast, accurate, et cetera. Because you know, the key, in order to correct all of these problems that I mentioned, this is not something that someone can rewrite every single time. This needs to be something that is really captured in robust software, right? And I think that that's one place where maybe I disagree with a few academics. I really think that, you know, at the end of the day, robust software is what will push forward science and scientific methods. So how do we actually get to a robust software that solves all these issues, so that way, you know, an undergrad could be doing all the different investigations that I showed before. That's what the core of the SciML or open source software organization is, where what we've done is we put together a bunch of composable tools for all of these different pieces. So things like, you know, embedding neural networks within differential equation solves, high performance, stable differential equation solves themselves, solving differential equations with neural networks, doing end modeling. So for example, chemical reaction network modeling tools, making sure that those are differentiable, making differentiable molecular dynamics simulators, differentiable climate tools, and also the tools for automatic identification of models, right? So turning neural networks into symbolic descriptions, right? There's actually over 100 libraries at this point that are all kind of built together to work together to be what solves these SciML problems. So what's going on behind the scenes? So let me kind of, this actually all started as just numerical differential equations. And a lot of people know by now that the Julia differential equation solvers, generally you'll see about 50 times faster than SciPy, and 50 times faster than MATLAB, and 100 times faster than DESolve. Like those numbers were kind of required to make this even possible for embedding neural networks, because if once you're trying to train a neural network in a differential equation, it's a very expensive process. But I think that the key to what's going on here isn't the benchmarks against MATLAB, Python, R, because you expect those you expect those three to be really slow, right? The key is really that there've been a lot of things going on behind the scenes to make sure that the Julia differential equation solves outperform the classic C codes and Fortran codes that have been used in the past. And I'll point to other things that talk about the aspects of how we're able to do this, outperform these aspects. I think that I gave a talk on differential equations in 2020 that describes a lot of the different tricks and techniques that are being used in modern differential equation solvers. And like this was kind of the bedrock that can then allow training, the scientific machine learning approach to be actually possible. So let me kind of showcase one aspect of that. So there's always this black box that everyone talks about in terms of software, which is, linear solves and matrix multiplication. That's always done by BLAS routines. It turns out that the open BLAS that is used by open source languages is not as efficient as people would let you think. That comes from the MIT Julia lab, actually. So the open BLAS, the BLAS that is behind a lot of other things like SciPy and such, that was created by the MIT Julia lab. We had the developer for a while, but we actually then decided that the actual way to do this better is to make use of code generation on demand, make use of compilation tools and JIT compilation to improve this. And so within the context of the differential equation solvers, we've recently showed that if you write pure LU factorization tools in ways that you're manually handling the assembly generation and the use of SIMD, you can actually outperform not just OpenBLAS, right, which is one of the standards that are used, but also Intel's MKL. So if you know about a lot of these details Intel's MKL is a very highly optimized BLAS library for Intel chips, but it's not very well, does not perform very well on AMD CPUs, which are right now the highest end CPUs. And so if you make use of, if you really spend the time to improve linear solvers under the hood, you can actually double, the flops over of this very crucial aspect, right? So this is like, there's other talks that will go into all these other details about performance, but details about how the LU factorization is performed, different ways of calculating floating point powers, all these little details come into play to be able to do the optimizations here. So when you see 100 times faster, don't think it's just one aspect. There's hundreds of things going on to give that number. I'm going to skip over the symbolic pieces and straight to this. So how is the SciML library actually working then for doing this fitting process? So we have it now so that way it's fully automated. So if you write one of these problems where you say, well, this is my differential equation that I'm solving, right? You just use the standard differential equation solver of the Julia language, and then you put a flux.train. So then you put the machine learning training framework on top of it, right, where this differential equation solve shows up in the loss function. If you do this, then on demand, it will actually do a code generation where it will take this ODE that it's solving and it'll create a backpass. It'll actually create a code for the backpass. It will JIT compile that code, and it will use that code for the calculation of the derivative through the differential equation solver, right? And so what this looks like in practice, for example, so here's fitting a neural ODE in a way that takes, just a few seconds. Once the compilation goes through, then you can see that it rips right through and it does this parameter estimation process. And the result here is a neural network defined by an ODE. So neural ODE is able to match this time series after, a sufficient amount of training, right? So this is something that you now can do in this is a half-minute process to train a lot of these. We mix this then with other ways of developing loss functions. So, always put this slide in here just so that way, everyone can know that, if you just put the loss function in just one solve, that's not necessarily stable. We have alternative papers that show that you can do things like multiple shooting and co-location methods and put this all together to improve the efficiency and the stability of the training process, though the discussion about what loss functions you use is almost like a separate topic from the differentiation, because as long as you differentiate the differential equation solvers, then you can always use whatever loss functions are useful for your case. So one of the things that we did was we made sure to develop new adjoint techniques that were robust to stiffness. That's a very detailed argument. So I'd refer back to that stiff neural ordinary differential equations paper that describes about the irreversibility. So even if you're using a stiff ODE solver, on stiff ODEs, you cannot necessarily do this reversing process. And so we developed different ways of doing that adjoint solve, which don't require reversing, but can also get you to linear scaling with the parameters, right? So all the way from cubic scaling with respect to the neural network weights to linear scaling with respect to the neural network weights by keeping the implicit portions separate from the neural network in details. So I'll refer to the paper for the specific details there, but I want to kind of show that, so not only are there stiffly robust adjoints, right, but there's also a lot of other adjoints you can come up with. So here, for example, is one that was gotten a lot of attention on Twitter because it's kind of a weird one, right? If you actually try to do automatic differentiation through a chaotic process, you'll see that automatic differentiation essentially fails, right? So there's two reasons to understand why it fails. So let's say you take a look at the Lorenz attractor. If you solve the Lorenz attractor and you have any little bit of error, then you will not be on the correct trajectory, right? So how would automatic differentiation even work if your solution is O of 1 off, right? You can't expect it to work in that case. Another way to think about it, though, is that the Lyapunov coefficient describes the exponential rate of the growth of the tangent space. And what forward mode and reverse mode automatic differentiation are doing are either pushing forward the tangent space or doing a pullback through the tangent space. And so if you have a chaotic system, then your tangent space is growing exponentially because that's what the Lyapunov coefficient is telling you. And so what you'll actually see from automatic differentiation tools, if you apply them to something like the Lorenz equation, you'll see that you just get this blow up of the tangent vectors, and it'll tell you that your derivatives are going to infinity. But it turns out there are ways to be able to correct for this. So if you know about the shadowing lemma, right, as you solve if you solve a chaotic differential equation, then as you go forward, your solution is not necessarily the solution of the ODE that you wrote down, but it is another solution that lives on the same attractor, right? In some sense, there's a shadow trajectory that lives on the same chaotic attractor that you will have found, which is why we know that the picture that was drawn for Lorenz equation is O of 1. It's a very incorrect picture, but the attractor that is finding is still the right attractor. That's due to the shadowing property, right? And so what you can do is as you take each step, you can actually create an ensemble of steps. So that way you kind of get an ensemble along the attractor, and then you can use a renormalization of this ensemble to give you an average derivative of these attractor quantities, right? So even though the derivative of the solution at a given time point is not well defined because you have exponential error growth, and so it's, the numerical value at a given time of a chaotic solution is not well defined. It's only really defined probabilistically. But since it is defined probabilistically, you can use this shadowing adjoint approach to be able to get derivatives with respect to the long time trajectory properties of chaotic systems. So this is, you can learn a lot more about this on the blog post all about it. But what this really shows you is that, there's not just, adjoints which are, efficient for non-stiff ODEs and adjoints for stiff ODEs, but also adjoints for chaotic systems, adjoints for, there's a bunch of different ways you can calculate this derivative. They're always making different trade-offs, and you need to provide a software, just like you give different ODE solvers. You need to provide a software that can give different ways to calculate these derivatives. And so If you actually look, I skipped over this little detail, but if you look at this, there's a keyword argument in here, which is sensalg, which lets you choose an adjoint approach. And so when it does this code generation process for how to calculate the derivative, it will generate different codes depending on the types that you've put in here. And so why do you need these different types? Well, it's because each of the different adjoint approaches make different trade-offs, right? So the backsolve adjoint approach from the neural ODE paper, I mentioned that its stability is poor, but you might want to use it in some cases because it has the lowest memory usage. It has O of 1 memory usage. And if you have a non-stiff ODE where it's Lipschitz constants are sufficiently small, this could be a very good performer. So, you want to be able to have this choice. You want to be able to have a choice of different, an interpolating adjoint, which is also stable, but requires some memory use. There's a version which requires even more memory, but gets much better compute performance, right? There's all this trade-off between memory, stability, and performance that's always going on. And so just like with ODE solvers, we created a system so that way, if you have different properties in your differential equation, you can choose these different ways to be able to do the adjoint calculations. And now, does this actually matter in practice, right? Like, that's, like I always like to, there are a lot of things that you can do mathematically that are just cool, but it doesn't actually, does anyone actually care at the end of the day? So let me kind of get to that by showing one bit about the adjoint, right? When you're solving this differential equation in reverse, the port that is actually carrying back the derivative of the solution with respect to neural network weights is called this adjoint differential equation. And so if you look at this, there's actually something called a vector Jacobian product here, which means you can actually calculate this vector Jacobian product as a push forward of u into this function f, and then you do a back propagation of this value lambda. So you want to use reverse mode automatic differentiation embedded into the definition of the derivative of an ODE. And then there's many different automatic differentiation things you can do, which some are specialized on highly scalarized code, others are specialized on more vectorized code. But so when we put this all together, when you look at like, okay, you have different adjoint techniques, but even when you write down the adjoint, there's a bunch of different ways you can do the code generation approach because of this vector Jacobian product. And when we actually took them all together, what we saw was that one of the key softwares that people used before for these adjoint approaches and defining derivatives of differential equations was Sundial's CVODES. And we saw that we can actually get about 3 orders of magnitude improvement when calculating derivatives of solutions of stiff partial differential equations by putting all these things together. So when we generate our adjoint, we're using a static vector Jacobian product, which is highly specialized on the scalarized codes that come from the stiff PDE, but we're also using a implementation of the adjoint, which instead of having cubic scaling with respect to parameters, it has linear scaling. And so when you put all these bits together, you don't get something that is just kind of like a 20% faster. You get something that is actually around 3 orders of magnitude faster. And that was actually something that we didn't expect, but when we saw that, it was very, very made us very happy, of course, right? But you don't think that this 3 orders of magnitude improvement is because of one paper or one thing that I've mentioned here. It's the improvement in the differential equation solvers. It's the improvement of using different adjoint approaches. It's the improvement of using different vector Jacobian products. Each of those bits, I guess losing performance is death by 1,000 cuts. So every little thing that is incorrect for this given equation, everything that you've hard coded, everything that you haven't used code generation for, will lose some performance. And so we've been kind of like chopping out and getting something faster and faster by not using one technique, but by giving an ensemble of techniques together and by giving someone the choice to be able to piece everything together. Of course, this ends up with another problem that we're having to solve, which is how do you automate the choice of this adjoint approach so that way, people don't have to know all the little details about the software to get all the performance. That's a whole another issue, which can be a whole talk in itself, because that requires using a compiler analysis of someone's ODE to be able to guess properties. And that's kind of like the fun next step. So if you see a talk in a year that talks about that, it's already starting now. But at the end, what makes the SciML system work and what made all those examples work, it really is this connection between all of the techniques of differential equations, so things like stiff ODE solvers and DAE solvers, and mixing them with multiple adjoint approaches so that way you can change the way you're calculating these derivatives. So that way we're using different ways of calculating derivatives for the climate techniques than we were on the epidemic models, because they have different properties, they have different things that have to be specialized on, just like you would specialize your ODE solver choice. And so, when we look against something like TorchDiffEq, like one of these Python packages for neural ODEs, we see a pretty tremendous difference at the end of the day in terms of performance. But again, this is not due to one factor. This is due to a congruence, all of these factors coming together in terms of, optimizing the differential equation solve and the derivative calculations. So is this actually being used in practice? Well, we see that, for example, people at NASA launch services have adopted this and saw 15,000 acceleration over what they were doing with Simulink before. We worked with Pfizer's system pharmacology group to get a 175x acceleration. And in fact, we're going to be following up then with a lot of scientific machine learning work with putting SciML into Pfizer's clinical trial pipeline to further accelerate it. But one of the big things that we've shown is, when I discussed that we do all this stuff in pharmacometrics, one of the key results that we have is that the Moderna vaccine and the fast clinical trials are part of that, right? It all came down to the fitting nonlinear mixed effects models. And when fitting those nonlinear mixed effects models, those derivative calculations use all of the techniques that I mentioned here at the end that were developed for the SciML libraries. So that was kind of like the key at the end, that doing things to be able to solve differential equations faster and be able to fit differential equations faster really did have a pretty tremendous impact out there. So I think that this is probably a good ending point. If anyone wants to hear this other story about something that's a little wacky, I can go through that. But if you have questions, I think is a good time for that now.
So Chris, thank you very much. A very impressive overview of all the work you did or currently doing, sorry.
Yeah, thank you.
Do you hear me, Chris?
Yeah, I hear you.
Okay, perfect. So I am opening the round for discussion. Yeah, Clemens Kreuz has a question, and we have a microphone too. Awesome.
So thank you very much for your interesting presentation. I have actually several questions, but maybe I start with a question about finding the optimal parameters, and especially is it, I guess that when you train your models, you have the mechanistic part and the neuronal network part. I guess the solution is not
I think
right. Is it? Can you hear me?
Yeah, your mic cut out for a little bit. Repeat the question?
So I guess that there are many different parameter combinations where the model fits very well to the data. How do you solve this issue? How do you find a final set of parameters? And have you thought about parameter uncertainties and also prediction uncertainties? I think both is somehow related.
Yeah. So I mean, in terms of uncertainties, you can use you can use uncertainties to be able to kind of do this, right? So I mentioned very briefly that everything that I'm showing here in terms of model discovery and everything, you can do in a probabilistic sense, where you do this in terms of a Bayesian fit, and you can say, are there multiple solutions for what possible missing terms are? What are the probabilities? And this will actually give you there's a 95% chance that you're missing a quadratic term, a 5% chance that you're missing a cubic term, right? So you can use a Bayesian type of approach as one way to get the uncertainties. I don't think, but I'm not completely satisfied with that, because there's actually a very, very more interesting question going on in here, right? So if you know about parameter estimation in the differential equation solver, without neural networks context, right? There's this idea of identifiability, right? Like, do you have sufficient information to be able to fully capture all of the parameters in your model, right? Numerical issues aside, could you have even found the right parameters in the first place? Now, we know that you're not going to have parameter identifiability when you put a neural network in here, because there are many neural network weights that will give you very similar neural networks, right? But if you're thinking about the neural network as a function, right? So there's many different neural network weights that might represent the same function, and so it's not parameter identifiable. But is that function itself identifiable? This idea of functional identifiability is something that we've been seeing in our work, almost accidentally stumbling on it, where in the cases of a lot of these nonlinear mixed effects models, right, we can actually show that we have functional identifiability in the sense of when we perform this training process, we do it Bayesian, et cetera, we always get the same exact function, though maybe sometimes it gives you a function that has different parameters each time. So in some sense, it's like, oh, there's some thing that is capturing, right? Like when it gives us the symbols at the end of the day, these might be identifiable even though the parameters of the differential equation are not identifiable. And so there's some form of functional identifiability that probably can be done to be able to formalize this a lot better. But we have not solved that problem yet. So where we are with that is, let me open up a site here. So inside of the SciML open source software organization, we do have a tool which we created for structural identifiability, where you can take any differential equation. So one's written as Julia or one's written symbolically. We can automatically turn them symbolic. That's a whole story itself. But we can perform structural identifiability with respect to parameters and be able to say, for this kind of, for a model with these inputs, these outputs, these states, and these observables, are things locally identifiable? Are they globally identifiable? Is this parameter not identifiable, right? So we have gone through and built the software to do those aspects first, because that has some theory and well-defined methods for it and everything. Now I want to go back, now that this is kind of built, we do want to go back and see how can we extend the methods for parameter identifiability to functional identifiability? A, is that possible? And B, what does that tell us about a lot of these cases where people are trying to use scientific machine learning? So great question. So it's definitely a work in progress, and I would definitely love to collaborate with anyone on this problem, because I find the idea just really cool that, maybe you can identify a function even if you can't get specific parameters that define the neural network of the function. So.
If there is no other question, I can maybe ask an additional one. So when you compared the performance of the ODE integration methods, I think this somehow critically depends on the accuracy of solving the ODEs, right? And this is, of course, controlled by some hyperparameters, integration tolerances, so absolute and relative and so on. Mm-hmm. I think, but these hyperparameters have different meaning in different methods, yeah? So if you have an absolute tolerance of 10 to the minus 6 in one integration method, it's not exactly the same than 10 to the minus 6 in another method, because step size control is different, for example. So how do you solve this? I think if you purely look, so there's
a standard way to do that. It is called the work precision diagram, right? So what you do is you solve the differential equation at a very, very, very low tolerance. So say you use something, we usually do this in extended arithmetic at 10 to the minus 16th. So we know that that's going to be more correct than any of these, any of the ones done with the standard floating point. So you get a very accurate solution. And then you solve the differential equation with the different methods at the different tolerances, right? And you look at what the error is against this truth data, right? And you can see that your truth is respectable because everything is converging to an error 0 as you decrease the tolerances, right? And so then, if you solve with Vern 7 in differential equations.jl, it gives you, for the same tolerances, it's about an order of magnitude different in the amount of error, but if you just look at a vertical line, this really tells you for this amount of error in the true solution, this is the time difference that you would have had, right? And so that's how you can kind of correct for that effect. And so, these work precision diagrams are all with respect to that effect. So as you have different methods, they will have different error behaviors, different time stepping. But what you really care about is if I needed to solve this equation, with error of essentially 1, in L2, this is how long the different methods would take, and that's really been the key.
Okay, thanks.
Hi, Chris. First of all, thank you for your talk, and also as a heavy Julia user, I want to thank you on behalf of the Julia community for the amazing work that you've been doing over almost the past decade, let's say. And you've even helped me out on the Julia Slack several times in my own package development. So big thank you. And to my question, so I'm aware that you've been doing a lot of work on stiff neural differential equation solvers in the past. And as far as I'm aware, there's also a lot of work going on in the modeling toolkit with automated transformations of ODE systems. And I'd be interested to hear your take on where the scientific machine learning field is evolving in the next, say, 5 years. So what do you think are going to be some developments that we will see in, say, the next 5 years?
Yeah, so this is the part that kind of skipped over that. Yeah, so we've been finding that, you know, like I mentioned a few bits how like, oh, there's something going on with the compiler doing code generation under the hood, et cetera, et cetera. But there's actually a lot more interesting stuff that you can do as you integrate compilers into numerical methods. I'd actually point to a blog post that, you know, if there's one blog post that I'm using to, I'm showing to all my new students to basically say, this is the kind of problems you should be thinking about. It's this one where with a very simple blog post, you can show that this idea from compiler analysis called non-standard interpretation, right? Non-standard interpretation is what gives you automatic differentiation. It basically allows you to do, you know, with non-standard interpretation, you could take a code for solving f of x and you can turn it in code for f prime of x, right? But it turns out that that's not the only thing you can do with non-standard interpretation. You can take a look at someone's code and automatically give the sparsity pattern with respect to the Jacobians. That's not the same as automatic differentiation because the global sparsity pattern is different than the derivative or the sparsity at a given point, right? So you have to do something a little bit different, but it's also a program analysis, right? Nobody should be ever having to tell you what the sparsity pattern is. You can look at their code and say, you know, variable xi never touches xj, right? You never add between them, you never multiply between them. So because they never touch, you have a true sparsity, a true zero over here, right? And you can do that through a compiler analysis. Uncertainty quantification, right? When people talk about methods for, so you have these methods like non-intrusive uncertainty quantification became really popular because you can use non-intrusive methods on black boxes. Right, and intrusive methods are things like you take this differential equation and you define a new differential equation that carries forward uncertainties, right? Well, it turns out that if you have compiler-based approaches, intrusive uncertainty quantification methods can be automatically done through compiler-level analysis. So this compiler symbolics can do these things that people would think of as a very manual process. Another thing is that, you know, things like automatically stabilizing someone's code by taking a look at their ODE and saying, this is a high index ODE, I'm going to change your differential equation solver code from this code to this code, right? That can be done automatically. And that's not even just in a symbolic sense. That's something that you can do on directly on their just pure Julia code, right? You can say, oh, if you have this interaction graph will give you a certain, it'll give you a singularity in your Jacobian. So if I actually differentiate and do some substitutions, here's a better differential equation for you to write down. This will be more stable. You should solve this one instead. And you can do that code transformation approach, just like automatic differentiation is generating new code, right? This kind of thing can be done automatically to someone's code. So I think that, yeah, where we're going in the future is we really, you know, maybe it's because I've been working with a bunch of compiler people, right? It's just, you know, in the Julia lab, everyone's writing compilers, and I just kind of see like, wait a second, like a lot of these things that we've been thinking of as numerical problems, right? You know, numerically solving a differential equation, where we just kind of say that we get whatever differential equation you give me, right? And I just try to numerically solve it. I think that's going to be the past, right? Incorporating the compilers into the way that we do the differential equation solving, changing your differential equation so that way it's better, changing your differential equation so that it includes uncertainty estimates. Like one of the big aspects here was when I said, oh, we change your differential equation, we build an adjoint equation, but we actually impose in that we actually use reverse mode automatic differentiation to define this adjoint pass better than you can do it numerically, right? And that's one of the big key aspects that is able to outperform sundials here, because sundials does this adjoint purely with a numerical Jacobian multiply, transpose and multiply. But if you allow yourself to do code transformations, you can do better, right? I think that that's really the future, just incorporating all of these ideas of changing someone else's code and the symbolic aspects of that. And using that as part of just the standard way you do numerics, so we call symbolic numerics. That is really what we're looking at as the future. So, so here's a diagram of what that all looks like. When we're looking at something like PDE constrained optimal control, a lot of things that we're saying is, they should probably be going through modeling toolkit first, which has an underlying, symbolic libraries under it, which is then generating numerical problems and using automatic differentiation. So, this mixture of symbolics of the compilers and everything with the numerical tools is where we're going. there's a lot of steps that we need to do to get there. And we know that a lot of the compiler tools are a bit finicky right now. Like most people probably couldn't use the compiler plugins right now. And automatic differentiation has weird failure cases. But in 5 years from now, I think that a lot of the things that we teach students to do today, like, oh, if you want your solution to be positive, you should exponentiate your terms, right? That's the kind of thing that we can automatically do. We can automatically say, oh, you want your solution to be positive. Like, I don't need to do anything numerically. I actually just change your code such that you're exponentiating and putting logs in the right spot. And now you're okay, right? And all those kinds of things can be done in with these future compiler approaches. So yeah, there's going to be a lot of fun things.
Okay, Chris, so thank you very much. In case there are no further questions, I just say thank you once more. Your work is appreciated and enjoyed here in Freiburg. And I would like to go to our next point then, probably.
Yeah, thank you.
Bye-bye.